Okay, I'm just going to quickly go through this 12.2 lesson here. Hopefully you did the warm-up. So again, on the warm-up, it asked you about the scatter plot. So there's a weak negative linear relationship. I didn't do a very good job of putting it in context here. So, you could say between weeds per meter and corn yield. Down below, so you have your HO is beta is equal to 0, HA beta is not less than 0, beta is the true slope of the regression of corn yield on weeds. Remember, it's always the y variable on the x. T-test for slope, it told me the conditions have been met. I just pulled both of these things out of the table. T, the p-value divided by 2. The p-value is less than alpha, reject HO. There is enough evidence to say that more weeds reduced corn yield. Can't talk. Okay. In this section right here, the idea here is that sometimes your data is not linear. So like this data set right here is definitely not linear. So if I look at this picture of this data set, you can see that there's not a linear pattern there. So if things are not linear, you have two choices. So one choice we have is that we could go through the list of regression options we have, and we could maybe pick one of the other regression options, quadratic, cubic, quartile, whatever. The other option we have is we take the data that we have and we transform it so we can still use this form of an equation that we had previously, okay? We're going to take the approach of transforming, and so we can still use our old familiar equation. All right, so a power model. So a power model is one that looks like y equals ax and raised to the b there. Or x is raised to the b's. So again, I don't have that y equals a plus bx form. An example would be this one right here. So anything that is increasing at some, the variable is increasing, there's, at a constant rate or whatever, at something I can raise to a power of. If you type this data into your calculator and you look at the scatter plot, you can see it looks like this. So there's a strong negative non-linear relationship between under 5 mortality rate and income per person. So what I'm going to do here is we're going to apply a transformation. You're not going to have to come up with the transformations on your own. Like the problem will already do the transformation for you. You have to just figure out what was done. So to do the transformation here, we're going to take the child mortality rate and raise it. Make sure you have a -1 there. We're going to raise it to the -1. So that's like just taking the reciprocal of the child mortality rate. So I'm going to take the reciprocal of the x variable. So if I go into my calculator, in that third list, I'm just going to do 1 divided by the reciprocal of the x variable. So I get those values there. So then in my scatter plot, instead of looking at the x variable, I'm going to look at the reciprocal variable. So I'm going to look at the reciprocal against the original y. And if I do that, lo and behold, my fit looks a lot more linear now. All right, and it's now positive. So I have a strong positive linear relationship. I don't really care if I changed it from negative to positive. That's kind of irrelevant to me. As long as I can make a better prediction, that's what's more important to me, okay? All right, when you're looking at these transformations, again, I told you, you're not gonna have to figure out what to do. It's gonna be done for you. You just have to know what was done. If you look right here, you can see right there, the x variable's been transformed. If you look at the residual plot, you can see in the residual plot, the x variable is no longer just under 5, it says reciprocal of under 5. And the second transformation, they did a switcheroo here. So instead of, they kept the x as is, but instead of y, they have 1 over the y. Again, if you look at the residual plot, you can see that this x variable is not changed, okay? Again, the idea here is that we change these variables so we can still use our familiar y hat equals a plus bx. So when it asks you down here, do the following for both transformations. So when it asks you to write the equation of the least square regression line, remember I'm still trying to use this familiar form to me, but maybe now these two variables have been transformed in some way. So when I look at number 1, so in number 1, the first transformation, we didn't change the y, So it's still just hat. And if you notice there, I just said y hat's the predicted income. The x we did change, but I can still, that's still my intercept and that's still my slope. So there's my intercept, there's my slope. But if you notice here, I didn't put x, I put 1 over x because I changed it. For the second one, I changed the y. So I don't have y hat now, I have 1 over y hat. Okay? Sorry, I have the big hat. It's hat 1 over y. I don't know how you'd say that. But again, I'm still trying to use this familiar form. So now I have my intercept plus my slope, and then I didn't change the x in the second transformation, so there's my x. Instead of like making myself crazy and defining 4 different variables, I'm just defining the base variables. It's a little bit easier in a situation like this. If I was only doing one equation, like if I only had one transformation, I might define the transformed variable instead of defining like the original variable. So I'll show you later on. All right, the next thing it says predict the income per person for Turkey, which had a child mortality rate of 20.3. So you're just taking that 20.3 and plugging it into, for x on your other page. So you're just plugging that in and you're solving it. Be careful, this one, the y's in the denominator. The next one, we're interpreting the r squared. So again, we're getting that r squared from our chart. So I've got 84.3, 92.1. So 84.3% of the variation, remember it's always, here's my y variable. So in income is accounted for by the regression of income, again my y variable, on the reciprocal or mortality rate. Because on this one I didn't regress on just the mortality rate, I regressed on the reciprocal of it. Okay, the other one, remember my y is the reciprocal of income. So 92.1% of the variation in the reciprocal of income is accounted for by the regression of the reciprocal income on mortality rate, okay? And if you wanted to, like, which one does a better job? Obviously, the second one seems like it does a better job than the first one. All right, when we are thinking about a power relationship, clearly there's many different options that power could be. We could square it, we could cube it, whatever. Like, there's so many options, so sometimes it's easier, instead of trying to figure out which power I'm going to choose, I'm going to maybe think about using logs or natural logs. So all the work I have here, I could have used the natural log. This said we could use natural log as well. So I could have used the natural log. Remember, the only difference between log and natural log is the base. So what I'm doing here is I start off with this power equation. So y equals ax, and the x is raised to the b. Remember, a and b are constants, x and y are my variables. So I start off by taking the log of both sides, okay? So I just log both sides. This right here is still log of y. If you remember your properties of logs, if you don't stress. I'm not testing you on the properties of logs. I'm just showing to you what happens here. So if you remember your properties of logs, I'm allowed to split those up. So I've got the log a, and then I got the log of x raised to the b. And then if you remember your properties, I'm allowed to pull that b down. So I end up with the log of y, the log of a, and then b log of x. Remember, these are variables. These are x and y's here. But the log of a is a constant. So if I take the log of a constant, I just end up with another constant. And I didn't get very original. I just kept the constant at a. Over here, that's a constant, that stays there. I can't change, the log of x is a variable. But if you notice here, this kind of looks like y hat equals a plus b x, okay? So what I'm essentially saying here is that if I start off with something like this, but if two things are going to follow a power relationship, then I can make the power relationship linear by logging, or again, natural logging, both of the variables. So if two variables have a power relationship, you can make the relationship linear by logging or natural logging both variables. Okay. Exponential, y equals a b raised to the x. So the power now is the variable. Back here in the power model, the power is a constant. In an exponential model, the variable is the power. Exponential models, your compound interest, radioactive decay, like anything, a lot of your half-life stuff in science or whatever. All right, this is what the exponential, sorry, so we have power relationships are exponential. That's pretty much what we're focusing on in this section. So here's your exponential. I'm going to do the same thing. I'm going to log both sides again. Again, I could do the natural log. I'm just logging both sides. If this breaks up, that x is going to come down. Okay, this is the variable. A is a constant, log of a constant, still a constant. Variable, log of a constant, b is a constant, log of a constant, still a constant. Okay, so in this one, if two things are exponential, I can make the relationship linear by just taking the log or natural log of only the y variable. Okay, so you're going to need, again, you don't need to know any of this stuff. If you don't remember your properties of logs, that's fine. But you should, this therefore stuff that I have here, this is what you should know and be able to apply. In this example, this is one about M&Ms. So the kid's got a bag of M&Ms. He dumps them out. So he's got the bag, he's starting with the bag of M's at start 0, then he dumps them out one time when in that first dump. He looks at the ones, he eats the ones that have an M on top, otherwise he puts the rest back. So the first dump he puts 30 back, then he's putting 13 back, then 10. So if you notice here, they're being kind of cut in half after each course. So an exponential model should describe the relationship between these two variables. If you look here, so the course, which is his dumping, on which he is, and the number of M&Ms remaining seem to follow an exponential relationship. So then, again, you're not going to be asked to look at this picture here and say, sorry, and say that this is exponential or this is power. But here it says after applying the natural log of the number of M&Ms remaining, here's the scatter plot of that versus course number. So you can see here they only did the natural log of the number of M&Ms remaining. If I look at the picture of the scatter plot, you can see in the title, only this one has been changed, okay? So would it be reasonable to use an exponential? So, I mean, I should add something here. Yes, the M&Ms should be cut in half, but, you know, the scatter plot shows a strong negative linear relationship. So if I look at that scatter plot, I can see that there's a strong negative linear relationship right there between those course and natural log remaining. Okay. If you look at the scatter plot, you're still not sure what they did. Look at your computer output. So here's the Minitab output. Again, you can see here only the remaining has the natural log. The course is still the same, all right? So they only changed that y variable here. When I want to write the regression equation, all right, again, in another example, I said, yes, you could take the log. Yes, you could use natural log. We're just going to think of them as interchangeable. You look at the problem and figure out what they did. This one, we did natural log. So I've got a big hat over the natural log of y, because that's what they took the natural log of. Here's the intercept. Here's the slope. The x variable wasn't transformed. This is an example of where I just defined the transform variable instead of defining the original variable. Either way is fine. The next thing says use your model from part B to predict the original number of M&Ms in the bag. So remember, my x variable is my course. It's not been transformed. So the original M&Ms in the bag is when I'm at course 0. So I'm plugging 0 into this equation down here. So 0, this goes away. Remember, when you have the natural log, to undo it, you got to e both sides. If you can't remember where that e button is, there's two ways to get to it. It's above the division or above the natural log. So second natural log, e 4.0593. So I get 57.93. So that's how many M&Ms were in the original bag. Again, it's a prediction. You don't need to worry about rounding. Here's your residual plot. So look at the residual plot. What does this graph tell you about the appropriateness of the model? So again, in the residual plot, we want no pattern. So a linear model is appropriate for the natural log of number of M&Ms remaining and course because there's no pattern in the residual plot. All right, how do you decide if a power or exponential model, how do you decide if a power, I don't have too many verbs in here, has been applied? Okay, again, you're not deciding which one to apply, you're deciding if what's been applied. So if you look at it and they did a log, natural log of both variables, it was a power. If you look at it and it was a log, natural log of just the y, it was an exponential. How do you determine which is better? So some other things you can look at. You can look at the scatter plot. You can just look at your correlation. You can look at r squared. You can look at the residual plot. Any of those things will tell you what's better. All right, we're going back to that under 5 child mortality rate and income per person, okay? So this was the first problem. If you notice here, here's the original scatter plot. Nothing's been transformed. If you look in the first graph, there's 2 different transformations, it says. So in this one, you can see here, the y has been transformed. In this one, you can see that both the x and y has been transformed. Which one shows a better linear fit? The second one. So that would mean the second one. So since I ln both, it's following a power relationship. So here, why is the power model would provide a more appropriate description of the relationship between income per person and under 5 mortality rate? Because this is, the scatter plot shows a stronger linear relationship, okay? Again, it says right here in the problem what they transformed. It shows you right here in the title how they transformed. You're still writing, so there's my big hat, there's my intercept, there's my slope, there's my natural log of x. Again, I defined the transform variables here. Here we're making a prediction for Turkey with an under 5 mortality rate of 20.3. So you're plugging that in here. Remember, you got to take, so if you're going to do it this way, so you could do 11.4950 minus 0.93740 times the natural log of 20.3. But that's that. I still have to undo, because it's a natural log of y is equal to that, so, or y hat, so I have to undo that. So that's how I got that number there, okay? And lastly, is the residual plot for part B is shown below. So this is just with this transformation, what does the plot tell you? So again, got no pattern there. So the power model is working well to explain, a power model would work well to explain that relationship, okay? All right, and that is your quick run through of that section.